So at this point, as a chemist, we can look at our values for delta H and delta S. And there was a guy by the name of Willard Gibbs who came along and he put a relationship together between delta S and delta H that allows us to calculate something called the free energy. And the free energy, sometimes referred to as the Gibbs free energy, is abbreviated with a capital G for Willard Gibbs. This is also an extensive property. So what we can say about this is that delta G naught is the free energy change when the reactants and products are in their standard states. And the next question we want to ask ourselves is, what are these standard states? So it depends what phase that we have. If we're dealing with solids, what we mean by standard state is that we have a pure solid at 1 atmosphere. When referring to liquids, it's going to be a pure liquid also at 1 atmosphere. If we refer to gases, we mean an ideal gas at 1 atmosphere. And if we're referring to aqueous ions in solution, we have an ideal solution at 1 molar concentration. So whenever we see that naught, this is exactly what we're looking at. And we're going to see then, a little bit later on in this unit, what happens when we change from these non-standard conditions. So Gibbs came up with some relationships, and the relationship that he came up with was that the free energy, or G, is going to be equal to H minus T times S. When we're looking at chemical reactions and we're looking at various systems, we typically want to look at the change in these particular quantities. So we also find that delta G is going to equal delta H minus T delta S. So this is our main relationship that Gibbs came up with. If we have our delta G equaling delta H minus T delta S, we need to come up with a way to predict whether or not a particular process is going to be spontaneous. So what we can do is we can manipulate around some of these equations. So what we're going to do to this first equation right here is we're going to divide by negative T. When we do that, we get delta G, or minus delta G divided by T, is going to equal minus delta H divided by T plus delta S. And this delta S is going to be the delta S of our system. We also know from our previous example that at constant pressure, the negative delta H divided by T is going to equal the delta S of the surroundings. So by manipulating this around, we know that negative delta G over T is going to equal the delta S of the surroundings plus the delta S of the system. Remember that we define the delta S of the universe to be the delta S of the surrounding plus the delta S of the system. So we can say, by manipulating these around, that our delta G is going to equal the delta S of the universe times minus T. Now we can come back to the second law of thermodynamics that says if we have a spontaneous process, our delta S of the universe is going to be positive. So if we have a spontaneous process, the delta S of the universe is positive, but we have this negative sign out in front here. So what we can say is that whenever delta G is negative, we're going to observe a spontaneous process. And this right here is going to be very, very important as we move forward. So this will allow us to predict in any particular instance whether we're going to observe a spontaneous process or whether that particular reaction is going to be non-spontaneous. So if we go back to the previous example that we performed, so our particular example, and if we say this example is performed at 25 degrees Celsius, that means we're at 298 K. We know that our delta G naught is going to equal delta H naught minus T delta S naught. All of our calculated values at the end of the textbook in the appendix are calculated under standard conditions. So here we can say that our delta G naught is going to equal the delta H naught value, which we calculated to be 85.5 kilojoules, minus T, which is 298 Kelvin, times 0.2115 kilojoules per Kelvin, and we have to convert that delta S value over to kilojoules. So this will tell us that our delta G naught, if we do the math, is going to be positive 21.3 kilojoules. So what we can say from this particular value is that this is non-spontaneous at 25 degrees Celsius. Okay, and the reason for that is that delta G naught is a positive value. Is there a particular instance where we could make this delta G naught negative? If we look at the math right here, we have a positive term for our delta H, and our delta S is also positive. So if this term right here can be made negative, so the more negative this term is, the more likely to be spontaneous. What do we have to do to make that term more negative? In this case, if we increase the temperature, that second term has a more likelihood to become negative.